At the end of this video, you should be able to list the rules for assigning oxidation numbers, give the oxidation number for each element in the formula of a chemical compound, and name binary molecular compounds using oxidation numbers and the Stock system. Chapter 7, Section 2, Oxidation Numbers. The charges on the ions composing an ionic compound reflect the electron distribution of the compound. In order to indicate the general distribution of electrons among the bonded atoms in a molecular compound or a polyatomic ion, oxidation numbers, also called oxidation states, are assigned to the atoms composing the compound or unit. Unlike ionic charges, oxidation numbers do not have an exact physical meaning. In fact, in some cases, they are quite arbitrary. However, oxidation numbers are useful in naming compounds, in writing formulas, and in balancing chemical equations. And as is discussed in Chapter 19 of your textbook, they are helpful in studying certain types of chemical reactions. Assigning oxidation numbers. As a general rule in assigning oxidation numbers, shared electrons are assumed to belong to the more electronegative atom in each bond. More specific rules for determining oxidation numbers are provided by the following guidelines. 1. The atoms in a pure element have an oxidation number of 0. For example, the atoms in pure sodium, Na, oxygen, O2, phosphorus, P4, or sulfur, S8, would all have oxidation numbers of 0. 2. The more electronegative element in a binary molecular compound is assigned the number equal to the negative charge it would have as an ion. The less electronegative atom is assigned the number equal to the positive charge it would have as a cation. 3. Fluorine has an oxidation number of -1 in all its compounds because it is the most electronegative element. 4. Oxygen has an oxidation number of -2 in almost all compounds. Exceptions include when it is in peroxides, such as H2O2, in which it has an oxidation number of -1, and when it is in compounds with halogens, such as OF2, in which it has an oxidation number of +2. 5. Hydrogen has an oxidation number of +1 in all compounds containing elements that are more electronegative than it. It also has an oxidation number of -1 in compounds with metals. 6. The algebraic sum of the oxidation numbers of all atoms in a neutral compound is equal to 0. 7. The algebraic sum of the oxidation numbers in all atoms in a polyatomic ion is equal to the charge of that ion. 8. Although rules 1 through 7 apply to covalently bonded atoms, oxidation numbers can also be assigned to atoms in ionic compounds. A monatomic ion has an oxidation number equal to the charge of that ion. For example, the ions Na+ or Ca2+ and Cl- have oxidation numbers of +1, +2, and -1 respectively. Let's examine the assignment of oxidation numbers to the atoms in two molecular compounds, hydrogen fluoride, HF, and water, H2O. In HF, the bond is polar, with a partial negative charge on the fluorine atom and a partial positive charge on the hydrogen atom. If HF were an ionic compound in which the electron was fully transferred to the fluorine atom, hydrogen would have a +1 charge and fluorine would have a -1 charge. Thus, the oxidation numbers of hydrogen and fluorine in hydrogen fluoride are +1 and -1 respectively. In a water molecule, the oxygen atom is more electronegative than the hydrogen atoms. If H2O were an ionic compound, the oxygen atom would have a charge of 2-, and the oxygen atoms would each have a charge of +1. The oxidation numbers of hydrogen and oxygen in water are therefore +1 and -2 respectively. Because the sum of the oxidation numbers of the atoms in a compound must satisfy Rule 6 or 7 for the guidelines that are found on page 216 of your text or on the screen still, it is often possible to assign oxidation numbers when they are not known. This is illustrated in sample problem 7-5 on page 217 of your text.
The oxidation number of any uncombined pure element is 0. For example, the oxidation number of these nitrogen atoms is 0. The oxidation number for the atoms of oxygen is also 0. The oxidation number of a monatomic ion equals the charge on the ion. For example, in a solution of sodium chloride, the oxidation number of the sodium ion is +1, and the oxidation number of the chlorine ion is -1. In binary compounds, such as carbon tetrachloride, the more electronegative element is assigned the number equal to the charge it would have if it were an ion. In this example, chlorine is more electronegative than carbon. As an ion, chlorine has a charge of -1. Therefore, the chlorine atoms in carbon tetrachloride are assigned oxidation numbers of -1. The sum of the oxidation numbers of all atoms in a neutral compound is 0. So the carbon in carbon tetrachloride has an oxidation number of +4. Similarly, the sum of the oxidation numbers of all atoms in a polyatomic ion equals the charge of the ion. For example, the sum of the oxidation numbers of the atoms in the sulfate ion must equal -2. Since each oxygen atom has an oxidation number of -2, and there are 4 of them, the sulfur atom must have an oxidation number of +6.
Using oxidation numbers for formulas and names. As shown in table 7-6 on page 219 of your text, or on the screen now, many nonmetals can have more than one oxidation number. A more extensive list of oxidation numbers is given in appendix table A15 on page 903 of your text. These numbers can sometimes be used in the same manner as ionic charges to determine formulas. Suppose, for example, you want to know the formula of a binary compound formed between sulfur and oxygen. From the common +4 and +6 oxidation states of sulfur, you would expect that sulfur might form SO2 or SO3. Both, in fact, are known compounds. Of course, a formula must represent facts. Oxidation numbers alone cannot be used to predict the existence of a compound. In section 1, we introduced the use of Roman numerals to denote ionic charges in the stock system of naming ionic compounds. The stock system is actually based on oxidation numbers, and it can be used as an alternative to the prefix system for naming binary molecular compounds. In the prefix system, for example, SO2 and SO3 are named sulfur dioxide and sulfur trioxide, respectively. Their names, according to the stock system, are sulfur 4 oxide and sulfur 6 oxide. The international body that governs nomenclature has endorsed the stock system, which is more practical for complicated compounds. Prefix-based names and stock system names are still used interchangeably for many simple compounds, however. A few additional examples in names of both systems are given on the screen now. At this point, you should be able to list the rules for assigning oxidation numbers, give the oxidation number for each element in the formula of a chemical compound, and name binary molecular compounds using oxidation numbers and the stock system.